Hi everyone, in this lesson we're looking at analyzing graphs of polynomial function. And we have the definition of a polynomial function right here. The most important thing to notice is that when we have a polynomial in standard form, the degree of the first term is going to determine the degree of the polynomial, and that's going to help us do the graphing. Now, the steps involved in graphing a polynomial function, one of the things we want to understand is the graph's end behavior. In other words, what happens on the ends of the graph. So for example, if we have the function y equals x squared plus 1, that graph is going to look like this. Right, now I just know that from experience, but you may not realize that. So what we would do is we would say, well, what's the degree? The degree is 2. 2 is an even number. The value of a, that's the value of this leading coefficient. The value of a is 1, that's greater than 0. So I know that the left end of the graph is rising and the right end of the graph is rising. It helps me determine the end behavior. Now, let's look at another example. Let's say that we have y equals x cubed. Well, again, I know from experience that that graph looks like this, but you may not realize that. So looking at this polynomial, the degree of the polynomial is 3. 3 is an odd number. The value of a is 1, that's greater than 0, so I know the left end falls, that's this, and the right end rises, that's this. So the first thing we will do when we're looking at the graphs of these polynomials is determine the end behavior. The next thing we'll do is we'll find the x-intercepts. That's pretty easy. We're going to set the polynomial equal to 0 and solve. We'll find the y-intercept by substituting 0 in for x. We'll determine if there's any symmetry. In other words, does the graph reflect over the y-axis, or does the graph reflect about the origin by substituting in negative x and seeing what the result is. And number 5, we're going to find the maximum turning points to determine extrema. So if f is a polynomial function of degree n, then there's going to be at most n minus 1 turning points on the graph. So what do we mean by a turning point? Like this is a turning point over here, this is a turning point. We have a graph of a parabola. We have one turning point right here. Number 6, find at least one additional point, pick a value for x, and substitute it into the function. So we'll want to pick an easy value for x, and then we're going to sketch the graph, and we're going to do this all without the use of a calculator. All right, so our first example, without a calculator, sketch the graph of the given function. First, we're going to determine the graph's end behavior. All right, so we know that n is even. All right, because n is the degree of our polynomial. The degree of our polynomial is 2. And the value of a, right here, that would be 1. We know a is greater than 0. So for this guy, we have this scenario right here. So for this graph, then we know we rise left and we rise right. The next part, find the x-intercepts by setting the polynomial equal to 0 and solving. And this polynomial is factorable, and the factors are x plus 5 and x minus 2. So we know that x equals negative 5 and x equal 2 are going to be the x-intercepts when we do the graph. So we're going to have 2 points, one at negative 5, 0, and one at 2, 0. Find the y-intercept by substituting 0 in for x. All right, we're going to put 0 in for x. So when we do that and we solve, we get negative 10. So we're going to have another point at 0, negative 10. Now we want to determine if we have any symmetry. All right, so we're going to substitute negative x into our function and see what we end up with. And what we want to do is we want to look at the sign changes. If all of the signs change, we have odd symmetry. If none of the signs change, we have even symmetry. And if it's like every other, then we know that we don't have any symmetry at all. So if we look at the new function, when we substituted in negative x, we get a positive, a negative, and a negative. And we started out with a positive, and a negative. So we had no sign change. Then we did have a sign change. So right there, we know we have no symmetry because either all the signs have to change, and that would be odd symmetry, or none of the signs change, and that's even symmetry. But we have every other here, so we don't have symmetry on this graph. So we're just going to say neither. Find the number of maximum turning points. All right, so the value of n in this case were degree 2. So we have n minus 1, so that's 2 minus 1. So we know we're going to have at most one turning point in this graph. All right, for number 6, we're going to pick at least one additional point. Not really sure what point I would want to pick yet. I want to kind of sketch out a little bit of what I already know. I already know from step 2 that I have intercepts at -5, 0, and 2, 0. So let me draw those in. I also know that I have, from step 3, I know that I have a y-intercept at -10. So let me add that. All right, now that I have some of my points plotted, I think I'm just want to look kind of in this area because my graph is going to be probably something like this. So I think I'll pick -2 for the additional point. And when I do that, I get a point at -2, -12. So let me plot that. Now I know my end behavior on the left and on the right is going to be rising. So that helps me do the last part of this and sketch my graph. All right, and that's the first one done. And just note your graph does not have to be to scale. We're just doing a rough sketch. Again, without a calculator, we're going to sketch the graph of the function. We know that we have a value of n equals 2. This is a degree 2. This is a quadratic polynomial, so that we know that n is even. And the value in front of our first term, the value of a is -1, so we know that a is less than 0. Since a is less than 0 and n is even, we're working in this scenario, so we fall on the left and we fall on the right. Find the x-intercepts by setting the polynomial equal to 0 and solving. I'm going to take the square root of both sides, so we're going to get x equals plus or minus 3. So we know we have x-intercepts at -3, 0 and 3, 0. We're going to find the y-intercept by substituting 0 in for x. And we do that, we get a value of 9, so we know we have a y-intercept at 0, 9. Now we're going to determine if there's symmetry, so we're going to substitute -x into the function. Just be really careful here, you have to use parentheses. And if you notice, this time we started out with a negative first term and then the constant was positive. And when we substituted in a -x and we simplified, we still have a negative first term and a positive constant. So none of the terms had a sign change. So we know that we have even symmetry, which means we're going to reflect over the y-axis. Number 5, we're going to determine the number of maximum turning points. That would be n minus 1. The value of n here, our degree is 2, so 2 minus 1. So we know we're going to have at most one turning point. find at least one additional point. I think I'm going to do what I did in the last graph. I'm going to sketch out some of what I have already and then decide what additional point to pick. All right, so I know I have x-intercepts at 3 and -3. I have a y-intercept at 9. And the additional point I'm going to pick, I'm just going to go with 1. That seems like the easiest, and that should fall into the range of where I think my graph is going to be drawn. So I'm going to put in a value of 1 for x. So at 1, my graph is at 8. So I have a point at 1, 8. So I'll plot that. I know that on the left and on the right, my graph is falling. The end behavior is falling. So I know that my graph is going to be going like this. So we'll just sketch that in. All right, so we've sketched the graph, and I just want to have you notice here that we do reflect over the y-axis. This graph is reflecting over the y-axis, the way we expected when we looked at step number 4. All right, we're moving on to number 3. Like I always say, you should try this one on your own and come back when you're ready. The degree of this polynomial is 3, so n is equal to 3. So since n is 3, we know that n is odd. The value in front of our first term is 1, and 1 is greater than 0, so we know that a is greater than 0. So on our table, we're looking at odd, a greater than 0, so we have this right here. So we know we fall on the left and rise on the right. We're going to find the x-intercepts by setting the polynomial equal to 0 and solving. And if you notice, we have a GCF. We can pull an x out of every term, and then we can factor the trinomial that's left. Right, so we have 3 solutions here. We have x equals 0 for this first guy, and you don't want to ignore this. Since we have this here, we know x is equal to 0 is one of our x-intercepts. X equals 4, and x equals -2. So that means we have 3 coordinates here. We have a 0, 0. We have a 4, 0. And we have a -2, 0. To find the y-intercept, we're going to substitute 0 in for x. We end up with the y-intercept at 0, 0. So that we have an x-intercept and a y-intercept at 0, 0. Now we're going to determine if there's symmetry by substituting a -x into our function. And that looks pretty messy right now. It's really hard to tell, so I'm going to simplify each term. Well, any time you have a negative number cubed, it stays negative. So when I simplify the first term, I get -x cubed. Now, when we square a negative number, we're going to end up with a positive result. So this part becomes positive, but this is going to stay negative. So the next term is going to be -2x squared. And then on the last term, we have a negative times a negative. That's a positive number. So that means we're going to have positive 8x. So if all the signs change for every term, it's odd. If none of them changed, it's even. So let's see. We had positive, negative, negative. Now we have negative, negative, positive. We had every other. So we went from positive to negative. Then we went from negative and we stayed negative. It doesn't work that way. If it's every other like that, that means we have no symmetry. So we'll say neither. Find the number of maximum turning points. In this case, n is equal to 3. So we have 3 minus 1. So we know we have at most 2 turning points in this graph. Find at least one additional point. I'm going to do the same routine that I did before. I'm going to plot what I have, and then I'll decide what point I'm going to pick. First, I'll plot all my intercepts. Now, those are the points that I have so far. And I know that my graph is going to behave I'm going to have 2 turning points, and I know that I fall on the left and rise on the right. So that could only mean that my graph is going to do something like this. All right. So I think I'm going to pick another point, maybe somewhere between 0 and 4. So I think I'll go with 2. So at 2, my y value is negative 16. So I'm way down here. This is not to scale. I'm just going to call this negative 16. And at 2, I'm right about here. All right, let's go ahead and sketch that. All right, so that one's done. And we just want to confirm we don't see any symmetry here. We don't reflect over the y-axis, and we don't reflect about the origin. So I think our graph is good. All right, that's all I have for this lesson. Thanks for watching. Have a great day.